This week, we are still going to talk about we're still going to talk about probability. So we're still on that section, but we're actually going to talk about a different type of probability that comes up, and it's a little bit less intuitive than the probabilities that before. I think before, when we found probabilities of combinations of things, we either like added the probabilities together or we did 1 minus the probability. Those were the only two things that we've done. We're actually going to focus on a different type of probability. And before I even go into what this is, I'm going to set up a scenario for you. Okay, so let's just pretend that we go to the doctor and we're sitting in the office and the doctor tells you 3 things. Okay, so the 3 things he tells you is there's this disease and it affects 0.1% of the population. So it's very rare. Okay, the second thing he says is there is this test for the disease and the test is 95% accurate. Now, what that means, we'll talk about later. The third thing he says is you did test positive for the test. Okay, so I have a multiple choice question for you. What's the chance we have the disease? We have 100%, 95%, 9.5%, or 2%. Okay, now don't feel dumb answering this question because I feel like it's not very intuitive with the information we have now. Who thinks it's 100%? All right, that one's a little bit easy to tell that's not the answer. Who thinks it's 95%? Okay, we got 1, 2, 3. Who thinks 9.5%? 1, 2, 3, 4, 5 people, maybe 6. Who thinks 2%? No one thinks 2%. Okay, I'm going to tell you what the answer to this question is. The answer to this question is actually 2%. Very not intuitive, right? It doesn't seem like the answer could be 2%. How could this test that's 95% accurate test you positive and you're still 2%? You still have a 2% chance of having the disease. That doesn't seem right. Okay, let me first tell you what the test actually means, and then we can figure out why it's actually 2%. Okay, so when I say 95% accurate, so for example, like when you take your COVID test or something like that and it says it has a % accuracy, all this means is if I gave 100 people the test, it will say 5 people, oh, sorry. If I gave 100 people the test, it's 95% accurate, which means 5 people will be told they have the disease. Now, this accuracy isn't like a set in stone definition. If you look at other like medical tests, this might not be what it means. But for this situation, let's just say that's what it means for something to be 95% accurate. Okay, 5 people are going to be told that they have the disease, whether they have the disease or they don't have the disease. Okay. Okay. Now let's say we have 1,000 people, and I actually drew all these people. Every single dot here represents a person. Okay. Out of these 1,000 people, if the disease affects 0.1% of the population, how many people would we expect to have the disease? Not 50. How would we find it? That's okay. It's okay if you don't know. We're not going to be doing this later in class. This is kind of more of a hard example. Well, the disease affects 0.1% of the population, right? Which means out of the 1,000 people, 0.1% of the 1,000 are going to have the disease, right? A way to write this is, let's write 0.1 as a decimal first, because it's kind of hard to deal with percents. To change a percentage to a decimal, what do we need to divide by? 100, and that gives me 0.001. Okay, so if I wanted to figure out how many people actually had the disease, it would be 0.001 times the amount of people in the population, which is 1,000. Okay, now if you ever do this in your calculator, you're going to get 1. Okay, so out of these 1,000 people, we're actually only expecting one person in this entire population to have this rare disease. Okay, so I'm actually going to highlight this person. Let's just say it's the first person. So let's say it's this person here. So that's the person with the disease. Only 1 out of 1,000. Okay. So if we expect one person to have the disease, how many of the 1,000 people are going to be healthy? Yep, 999, right? Everyone else is healthy. Only one person has the disease. Okay. Now we have a 95% accuracy, which means out of 100 people, 5 people will be told that they have the disease. How would we find how many people out of the 1,000 people would have the disease? Or would be told they have the disease, sorry. So out of 100, 5 people were told, which means 5% of the people are going to be told that they have the disease. So maybe out of the 1,000 people, we need to find 5% of those. Okay, so I need to find 5% of my 1,000 people. 5% is 0.05. 1,000 stays the same. So 50 people, which is where you got 50, will be told that they have the disease. Okay, and that probably includes the person with the disease, right? So in my picture, I'm gonna square off 50 people. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. I think that's here. So in this test, okay, we have 1,000 people. 999 of them are healthy, but 50 of these people are going to be told that they have the disease, whether they have it or they don't. Okay, so there's going to be some healthy people that get what we call a false positive. Okay, so they're going to be told they have the disease, but they actually are healthy. Okay. Now, thinking about the question again. Let's say I'm one of those people who tested positive. Okay, but I don't know if I have the disease or not. What's the chance that I actually have the disease? Yep, 1 out of 50, right? Because I already know that I tested positive. I don't care about the rest of the population. I care about everyone who got told that they did have the disease. So if I'm one of those people, 1 out of 50 is 2%. Okay, so that's how we got 2%. Okay. So the idea of conditional probability, which is what we're dealing with, is we have a population and we're kind of restricting the population based on, for example, being told that we tested positive. Okay, we want to find the probability of something given the information that we already have. Okay, we call this conditional probability, and we have this weird way of writing it. Okay, so conditional probability deals with an event E and an event K. E is what we're interested in. So in the example with the hospital or the doctor example, we wanted to know if we had the disease, right? So E was having the disease. Okay. But we already know that K is true. So K is something that we already know about our population. So we're kind of restricting it. In this case, K was being told that we tested positive, right? So told that they tested positive. We were asked the probability that we had the disease, given that we already know, or that we already knew that we were told that we tested positive, okay? If we want to find this probability, we say the probability of E or having the disease, given that we're already told. So E given K. And we use this weird notation. So P always stands for the probability. So the probability of E, this line means given, and then K is the next probability. Luckily for us, we don't actually have to do the whole drawing the dots and circling what we're interested in to find the probability, because we actually have a formula for this, okay? Now, this is the formula, and it looks a little bit weird because I don't like variables and weird symbols in my formulas. I like to just write out what it means. So on top, I'm gonna say we're gonna count the number of outcomes where both E and K are true. Okay, so it's basically the amount of times we see both E and K at the same time. Okay, and in the denominator, we're going to have the number of outcomes where just K is true. And that kind of made sense with the hospital example. We counted the amount of people that both had the disease and were told they had the disease, and we put it underneath the number of people that were told they had the disease. Okay, now I know this looks really abstract. I do want you to either memorize this formula or know how to find conditional probabilities, and it might make more sense in the example, but I'll write memorize if necessary. Okay. The second thing I want to say about these problems is it takes a lot of work to be able to conceptualize the question. And to me, it's easiest to solve these types of questions if we have some sort of organizational system. Okay. In this case, I like to make these things called two-way tables. Okay. And let's just see what that is with an example. Okay. So here we have an example. We have an ice cream shop, and the manager of the ice cream shop wants to know which customers are buying which types of flavors. Okay. So what he did is he surveyed a bunch of people. He asked them, are you an adult or a child? And then they asked them, okay, did you order vanilla ice cream or chocolate ice cream? Okay. Let's assume that everyone ordered just like one type of ice cream and that's it. Okay. In this chart, we have this thing called a two-way table. Because there's two different variables being expressed in this chart. On the top, we have the amount of people who got vanilla and chocolate. And on the bottom, it describes if someone's an adult or a child. Okay. Now, I left the totals blank because based on this information, we can actually find the total number of people in each category. Okay. In this category here, let's start with this box. This total represents the amount of people in row 1, or the amount of adults. Okay. So how would I find this total? Yeah, add 52 plus 41. And that gives me 93. Same thing goes for children. Okay, I can add 26 and 105. And I think that gives me 131. Okay. So 93 and 131 represent the amount of adults and the amount of children. Okay. Now, let's go to the bottom boxes here. The one I just highlighted here is underneath vanilla, okay? 52 represents the amount of adults that like vanilla. 26 represents the amount of children who like vanilla. How would I find the total? Add them together again, right? So 52 plus 26 gives me 78. And then the same thing goes with the chocolate. So 41 plus 105 is 146. Okay. Finally, this block represents the total amount of people that were sampled. Okay, so it represents the grand total. Any ideas on how to find this number?
78, 146.
Okay, I can add 78 and 146, and that gives me 224. Yeah, right. You can also add 93 and 131, right? So I'm going to write a little note here, or 93 plus 131. That gives us the same answer, right? Now, what I like to do is when I find these totals, it's a good way to check to see if you're on the right page. If you add down and add across, you should get the same number. If you're not getting the same number, you might want to check your calculations again. Okay. Any questions so far? Okay. Now, when we have a table like this, it actually makes it really easy to find conditional probability. Okay. And before we even get to conditional probability, let's see how we can find normal probabilities with this table, okay? Part A says, let's find the probability of selecting a random person and it's a child, okay? You need a fraction, right? Now, what number do you think should go on top? 131, and why is it 131? Yeah, we're interested in selecting someone and it happening to be a child, right? So we should have the total number of children up top. So this is child. What should go on bottom? The entire total, right? We want to find, if I were to do this experiment, I want to find the probability of selecting a child out of the entire population. 224 goes on the bottom. So this is the total number of people. Okay, once you're here, I don't really expect you to simplify the fraction. If you want to, you can, but I'm really simple and I like to just keep that fraction by itself. Okay, let's move on. Let's find the probability that we select someone who is an adult and who also likes chocolate, okay? We need a fraction. What should go on top here? 41, right? Because that's what we're interested in. We want to find the probability of getting an adult who also likes chocolate. Okay, what should go on the bottom? 224, right? We're still interested in taking an adult who likes chocolate out of the entire population. Okay, so this would be the total. Any questions so far? Good. Continuing on, now we're getting to the conditional probability. And the way I know this is conditional is because there's that solid bar in the middle. Yep. So I want to find the probability of selecting someone who likes vanilla, but I already know that they are an adult. Okay, so I'm not selecting someone out of the entire population. I'm actually selecting someone out of the adults. Okay. Now you can use your formula or you can kind of think about this conceptually. Because I have the formula, let's just use it, okay? So in this case, E is liking vanilla and K is being an adult, right? Up top, we have the number of people or the number of outcomes where both E and K are true. So on top, I need vanilla and adult, right? And 52 is perfect, yep. Now on the bottom, the formula says we need to focus on just K, so just adult. And how many adults total are there? Is it 78? Actually,
one across 93.
It is 93. Okay, good. I usually make mistakes when I write my thing, so I was like, I wonder if that's actually true. All right, so our total probability is 52 over 93. Let's do it one more time. We want to find the probability of getting a child given that the child already likes chocolate. So E is child, K is chocolate. Up top, what am I looking for? 131, which is not quite on top. Remember, the top is both E and K. Mhm. Perfect, 105. And that's because we're looking for both E and K, which is child and chocolate. Okay, well, what are we having on the bottom? That's the not quite 131. I know it's hard to look at. Is it 146? Yeah, because chocolate is on the bottom. Yeah, so the one on the right goes on the bottom. Mhm. We're getting there. Okay, before I go to the next page, I want to talk about one thing about conditional probability. The order in which E goes first and K goes second, that actually matters, okay? And the way I know this is because what if I wanted to find the probability of chocolate given child? Okay, if I found this one, chocolate and child would go on top, which is what value? 105. So that's Choco plus child. Okay, and on the bottom, we are going to have not chocolate, but child, right? And how many children are there? 131, good. Okay, so if we look at this, and if we switch around the placement of E and K, the probability actually does change. Okay, so it does matter that you put the second one on the bottom and both of them on top. Okay. Any questions on what I did on example 1? I think it's a little bit less intuitive than regular probabilities. You have to think a little bit more and be way more careful with the organization. But I think once we get the hang of it, it actually isn't that bad. How about you try example number 2? Very similar to what we did before. And we'll come back in a tiny bit. Let's come up to the front here. As I walked around, I think everyone was on the right track. Mainly, I think, since this is such a weirdly worded question, it gets a little confusing. But I think we all did a good job. So in this example, we have students at a school. Some of them are taking math or not taking math. And then others are taking English or not taking English, right? Okay. So who wrote up the totals? Was that Alex? Do you kind of want to explain how you wrote up the like total values? How about this? Why don't you explain how you got 56?
So I just added 29
Mm-hmm.
and then 137 is the same thing, but with 95 and 42.
Mm-hmm. And then I bet you did the same thing on the bottom, but you added down. And then how did we get 193?
I added 56.
Good, right? Alternatively, you could have added the bottom 2 numbers as well. Any questions on getting the numbers? I think we're all good doing that. All right, going down to part A. That was Kelly. Do you want to explain how you got not Julie? I get you guys mixed up. I don't know why. Do you want to explain how you got the probability of taking English?
So I first did the total of how many people.
Mm-hmm.
And then I put it over
Perfect, right? We're taking someone out of the entire population if we wanted to find this probability. Any questions on part A? Sounds good. Part B was the probability of not taking math and not taking English. Who wrote up this one? Was that Megan? Do you want to explain how you got this one?
Yeah, I looked at the chart of who was not taking math and not taking English, and it went to 42. And I just
Mhm.
put that over the total one.
Perfect. So up top, not math and not English. Bottom is the total. Any question on part B? Perfect. Part C was a conditional probability, which meant we have that bar in there. Oh, Paris, did you have a question?
How do we know if 193 or
Okay, I would say the bottom number is always going to be the total as long as you don't have that bar. Okay, so the bar restricts how who we're taking the person out of. I would say for this one, I would think of, okay, if I was doing an experiment and I wanted to know how many people out of the entire total who are not taking math and who aren't taking English, I would collect everyone in the school and pick a person out, right? And that's why the bottom is going to be the total. If you don't want to think of it that way, I would say if it's not a conditional probability or the bar is not there, the bottom is going to be the total. Okay. That was a good question though. Any other questions? Sounds good. Part C was a conditional probability. We wanted to find the probability of taking English, given that we already knew that the person was taking math. Who wrote up this one? Was that Hope? Do you want to explain how you got this one?
Yeah, so
Perfect. So since this was a conditional probability, the number on the bottom is the second version or the second value, and then the one on top is both. Great job, Hope. Any questions on part C? All right, part D, taking math, given that we took English, so we switched around part C. Who wrote up this one? Was that Emily? Do you want to explain how you got this one?
how many people take
Perfect. Okay, so it's the same as part C, but the bottom is different. Part E was a different conditional probability. We wanted to find the probability of not taking math, given that we were taking English. Who wrote this one up? Was that Ashley? Do you want to explain how you got this one? Perfect. So on top, not math and English, and on the bottom was just English. Okay. Any questions on finding conditional probabilities? I think it's a little confusing at first, but I think the more practice we do with this, it gets a little bit easier. Next class, we'll talk about not just two-way tables, but like different types of tables with more numbers in it. It's basically the same process, but it'll give us a little bit more practice with conditional probability.